We're now going to look at a couple of theorems that have to do with some derivatives. So we'll start with Rolle's theorem. We start by assuming that we have this function that's continuous over some closed interval a to b and differentiable over the open interval. So as of right now, whether these are open and closed is not going to make too much of a difference. The main thing is we need a continuous differentiable function. We also need the endpoints of this function, f of a and f of b, to be equal to each other. Then we know that there is some point x0 in this interval such that the derivative is equal to 0. So I'm going to do a little bit of a proof by picture here. I'm going to kind of draw a picture and kind of explain how we know this to be true. So here I have a picture of a plane. I have some points A and B. We don't really know if they're positive or negative. I made one positive and one negative here, but ultimately it doesn't matter. We also know that f of A has to be equal to f of B. So we know these 2 points have to be equal. Well, there's a couple of different ways we could connect these continuously. We could draw a straight line, and the derivative of a straight line is equal to 0. So if this is f of x, then f prime of x has to be equal to 0. So there is definitely a point where the derivative is equal to 0. It's always equal to 0. But what if we don't have a straight line? Well, we know this has to be continuous, so we can draw as much as we want in the middle, as long as we have our starting and ending points. Well, like we discussed before, all of these maximum and minimums here, in this case I have 4 total, all of these points have a derivative of 0 because maximum and minimums only occur when the first derivative is equal to 0. So we must either have a flat function or we must have a maximum or a minimum, provided that those endpoints are equal to each other. Now that we have Rolle's theorem, let's move on to our next theorem. The next theorem is called the Mean Value Theorem. So first we need our conditions. Just like with Rolle's theorem, we need our function f to be continuous over some interval and differentiable over some interval. We're essentially just going to take away the condition that the endpoints are equal. We no longer need that. Then we know there's some point x0 in that interval where the derivative at f prime of x0 is f of b minus f of a over b minus a. And this looks complicated, and if you go on to Calculus 2, you'll see another version of the mean value theorem. But essentially, we're looking at an average value. There's some point where my derivative is equal to the average value of the function. And this seems complicated, and I'm not going to deal with an exact proof here, but the main question is why might we ever need this? What is the purpose of it? Well, 2 mathematicians named Purcell and Warburg wrote in a paper about the mean value theorem, and one of the quotes is, "The mean value theorem is the midwife of calculus, not very important or glamorous by itself, but often helping to deliver other theorems that are of major significance." So essentially what we're saying here is that this theorem alone isn't super useful by itself, but it helps us be able to develop other theorems in calculus that are very useful. And I'll give one of those theorems now. Let's start by assuming we have this function and the derivative of this function is 0 at every single point in our interval. Then we know that our function is constant over the interval a to b. And this is actually a very big deal. We talked about how the derivative of any constant function is equal to 0, and now this tells me that if the derivative is 0, I know for a fact it's a constant. Constant functions are the only thing that have derivative 0. And this actually comes as a result of the mean value theorem.